In the previous lessons, we learned that most of the elements on the periodic table, they are unstable. Now, what do we mean by unstable? Well, in order to be stable, the outermost ring, if you notice right here, that here we have electrons, right? They are located in different orbitals. And notice how I draw them together because they are in these specific orbitals, right? That belong to a specific energy level. And if you notice, there are different layers. Here we have one shell, second shell, and this is the outermost shell. This is also known as the valence shell. Or if we're looking at the electron right here, that is considered as the valence electron or the outermost electron. Okay, so another word for valence is outermost. Okay, so that would be outermost electrons. Now, by looking at the number of outermost electrons, we can actually determine if the atom is stable or not. In order to be stable, they need to have a complete octet, which is octet, think of the word octet. Well, that prefix right there is equal to 8. So if they have more or less than 8 valence electron, or the outermost electron, they would be considered as unstable. So to be stable, atoms need to find different ways to get a complete outermost shell, which is exactly 8 valence electron. Except for helium and hydrogen, they only need 2 valence electrons. So in this case, I'm looking at chlorine. Remember, chlorine is in group 7A, and the group number represents the number of valence electrons. In this case, 7A, so it has 7 valence electrons. So how many more? If you have 7, right? You have 7, how many more do you need to be stable? Of course, 1 more. That will give us 8. Where over here we have sodium, right? Sodium is in group 1A, and again, the group number represents the number of valence electrons. In this case, all the elements in group 1A, which including sodium, will have 1 valence electron. So sodium in this case, if you notice, you look at this carefully, it has multiple shells, right? So what it's going to do is going to give up that electron to chlorine. So in this case, chlorine will gain, right? And this case will lose its electrons. And in this case, both of them will become stable. One give up its electron, the other one gain. And once it gain one more, it has now an octet. With sodium, once it lose all of its outermost electron, now if I were to cover this up, guess what happened? The next inner shell becomes the outermost shell, because this shell no longer exists anymore, because there are no electrons in it. And we call this ionic compound, or in the process of this, call this ionic bonding. Okay, so that's what we have learned so far. Today we are going to look at another way that atom can react with another atom to become stable. And again, to be stable means to have a complete outermost shell. And in order to understand that process, we are going to learn about the Lewis dot structure. More importantly, we are going to learn how to interpret the Lewis dot structure. Well, let's look at bonding overview. Now, bonding is basically atoms react with other atoms in a chemical reaction. And basically the word chemical reaction means atoms react with another atom to become stable. And that's all it is. And of course, in the process, the main goal of the chemical reaction is to have a stable outermost shells. And all the atoms in that chemical reaction will have a stable outermost shell. And the process of atom either transfer, which we just talked about right here, right? Or share their valence electrons, which is the main topic for today. The whole entire process is called bonding. So bonding is a process where atoms either transfer or share their valence electrons, which is chemical reaction. And in the previous lessons, we learned about ionic bonds. And ionic bonds is basically atoms form either negative or positive ions. Now, how does it form a negative ions? Well, it's gonna gain electrons. Where the positive is when an atom's gonna what? Lose electrons. So when atoms gain or lose electrons to form a negative or positive ions, atoms have gains or lost their electron. And in the process, you notice you have a negative and a positive. When you have a negative and a positive, just like a magnet, when you have a north end and a south end, what happened to it? They would attract. And we call this electrostatic attraction. It's basically attraction based on the charges of the particle. So in this case, we have positive would attract to negative. Likewise, negative would attract to positive. And the attraction between the positive charge or positively charged cations, that's the word for positive ions, and a negatively charged anions, this is another word for a negative anions. So positive and negative. So positive and negative attract together. This electrostatic attraction is strong enough so that they will form a new, this is completely brand new and actually stable compound. And that's the reason why the majority or most of the substance that we expose in our life, they are actually compound. They're not pure elements, okay? And the one that's pure element are very rare, like gold even, or like diamond. They are extremely rare and they are extremely valuable. And of course, they would have a completely different physical and chemical properties, completely different from its atoms. Now today we are going to look at covalent bond. And what is a covalent bond? Well, a covalent bond, we talk about transfer in ionic bonds. Now in covalent bond is the last part, which is sharing electron. Well, in a covalent bonds, two atoms share their valence electron. Because they are sharing their valence electron, right? Each of the atoms will count the share as part of its valence shell. We will talk about that later. So in this case, sharing valence electron is another way that atoms can react with each other to have a complete outermost shell. That is a complete valence shell, which is equal to 8 valence electrons. Before we look at an example, we need to realize that this type of bonding only happened between what? This only happened between two nonmetals. This always happened between two nonmetals. So let's look at an example. In this case, we have a reaction between oxygen and hydrogen. Well, in this case, I draw the Lewis dot structure for hydrogen and oxygen. And for oxygen, you notice it's in group 6, so of course it's going to have 6 valence electrons. And for hydrogen, it's in group 1a, so therefore it's going to have 1 valence electron. But what's the magic number? They need to have 8. Well, for hydrogen and helium, it's only need 2. So in this case, if you notice, what can they do? They can share, of course. So if I were to take a substance of hydrogen and mix them with a bunch of oxygen, this is what they're going to do. Look at their valence electron. The hydrogen and the oxygen will attract together. Okay, this is the attractive force right here. They will attract to each other by sharing the electron. In this case, if hydrogen and oxygen share one more electron, and hydrogen and oxygen share one more electron, so that gives us a total of 2 electrons for oxygen. And this is what we're going to have. See this red electron right there? That is the electron that's being shared. And if you look at the overall compound that's being made from this chemical reaction, notice how this belongs in a specific place. That tells you that this electron will share between oxygen and hydrogen at this specific bonds right there. And what do we use to represent a bond? Well, if we look at the next picture, look what do we use to represent a bond? Right there, just a line. Those are chemical bonds. And they have specific name for it. There are 3 types of chemical bonds. This right here is considered as a single bond. What is a single bond? Well, single is 1. That means it's only 1 pairs of electron. What about 2 line? What is going to be represent 2? Of course it's going to be double. And double tell you there how many pair? 2. So there's going to be 2 pairs of electron. And then we have triple. Well, you couldn't get easier than that, right? Triple electron. 1, 2, and another one. Of course, triple, 3 pairs of electron. But what about these right here? What do we call those? Don't we have a name for it? Yes, they do. They are the lone pairs electrons. Why are they lone pair? Think of the word lone. They are very lonely. They're not sharing with anybody. They are by themselves. So this is considered a lone pair. Now, here's one thing tricky about the lone pair. Here's a tricky thing about the lone pairs of electron. Is that sometime in a Lewis dot structure, we don't have to draw the lone pairs of electron. That means you have to figure out that it is there. So if we look at hydrogen and oxygen here, another way of drawing that would be this. So this is not always drawn out for us, okay? So be careful with that. So another way of writing a Lewis dot structure for water is this. We would have oxygen, hydrogen, and hydrogen. Notice the lone pairs are not there, okay? So be careful with that. So we have learned that atoms will share electrons to become stable, and in the process they make single bond, double bond, triple bond, and the pairs of electrons that are not bound to another atom, we call those lone pairs. Now our job is to look at a Lewis dot structure and able to identify or able to describe the properties of that specific atoms in a Lewis dot structure using the components of Lewis dot structure. So let's look at the first atom. In this case, the first atom is what? Is oxygen. And of course, oxygen, this is oxygen, has what? It has 1 single bond. I'm going to abbreviate everything, okay? And how many double bond does it have? Of course, it has 0 double bond. How about triple bond? It doesn't have any triple bond. So in this case, it's going to have 0 triple bond. How about the lone pair? 1, 2, 3. So it has 3 lone pair. Want to try another one? Let's try number 3. How about that? Let's look at the third atom. Well, in this case, the third atom is nitrogen. And nitrogen has what? Nitrogen has, it has 2 single bond. It has 1 double bond right here. And it has how many lone pair? Does it have any triple bond? No. No, 0 triple bond and 0 lone pair. So before we move on, let's check it. That each atom in this Lewis dot structure actually has 8 valence electrons. Well, let's look at oxygen, right? It has 1 single bond. That tells you there are 2 electrons right there. And it has 0 double and 0 triple, but it has 3 lone pair. That tells you there are 6 of those electrons. So what's 2 plus 6? That gives you the magic number of 8. Let's try nitrogen. Nitrogen has 2 single bonds. That tells you there are 4 electrons total. And it has 1 double bond. Remember, a double bond is 2 pairs of electrons. 1, 2, and there you go. We have 8 valence electrons. And that's how you describe an atom. Before we move on, what does this charge represent? In order to be negative, you have to gain the negative particle, which in this case, the negative electron. So it is gaining how many? If there's no number there, that tells you there has to be 1. Okay, if it is a number, it will be that particular number of electron. If there is a positive charge on this particular compound, that tells you that it has lost a particular number of electrons, okay? So keep that in mind. Now, how can this be written in a different way that we don't show the lone pair? Remember, the lone pair It doesn't have to be drawn all the time. So all we have to do is this. Double bond. And we use the bracket to indicate that this has a charge. In this case, it has a charge of minus. And that's all we have to do. But you have to realize that by looking at this right here, you have to realize there are 1, 2, and 3 lone pair in order to be octet. Where right here, there need to be 2. And right here, of course, 1, 2, 3, 4, 5, 6. How do I know that? Based on the total number need to be 8 electron total.